All right, it's time for a new Bitcoin whiteboard video. For the past handful of months, I have been really wanting to do a whiteboard on shielded CSV. This is a new protocol that will allow us to bring perfectly private, cypherpunk level private payments to Bitcoin. If you're watching this video, you may already be familiar with things like Chami and eCash. So we have protocols like Cashew and Fedimint, which allow private payments with Bitcoin. However, those solutions are fully custodial. So in theory, they could be used to steal money or censor transactions or fractionally reserve the underlying Bitcoin. With something like Shielded CSV, we can build these private payment protocols in a fully self-custodial way. So in theory, I think most people would agree that this is like a strictly superior improvement when it comes to bringing these, again, like perfect privacy, fully shielded transactions to Bitcoin payments. Shielded CSV was introduced earlier this year in a research paper that came from three researchers, Jonas Nick over at Blockstream, Robin Linus, who invented BitVM, and then Liam Egan, who is the chief cryptographic scientist with us over at Alpen Labs. So in this video, I'm going to touch on a couple different topics. We're of course going to discuss like privacy and how shielded CSV creates private Bitcoin transactions. We're going to talk a little bit about Bitcoin L2s because shielded CSV would have to be a layer 2 protocol built on top of Bitcoin layer 1. And then what might be interesting is as we go throughout this whiteboard, consider the implications that shielded CSV could have for the kind of mounting kind of culture wars that are happening in Bitcoin right now. Specifically, a couple of years ago, ordinals busted onto the scene. People discovered that they can embed inscriptions or arbitrary data into Bitcoin, and that caused a lot of people to start putting JPEGs and NFTs and dick butts and all sorts of arbitrary data on top of Bitcoin. And there's a contingent of Bitcoiners who are very loud and very much against this activity because it is not monetary in nature and it detracts from Bitcoin's ability to be money. I think a generous interpretation of what these people may say is that technically, you might not be able to block or prevent this data from going onto Bitcoin, but we should not create a culture and a community that fosters and harbors this kind of behavior. We should do everything in our power to kind of make it difficult to post this type of arbitrary data onto Bitcoin because we want to champion the creation and build out of Bitcoin as money. Like that is the true, revolution that's happening here. Where shielded CSV might make this interesting is we have this ability to introduce this really badass monetary application that is super aligned with Bitcoin ideals and ethos. But you will see in this video that it benefits and arguably requires the ability to post some amount of arbitrary data into the Bitcoin L1. And so I think there will be a point where people are going to have to kind of like face this reality of, okay, do we want to build out these really badass, cool monetary applications for Bitcoin and accept that people need the ability to post data into the Bitcoin layer 1? Or do we want to, at all costs, like dissuade and try to block arbitrary data, which could impact our ability to build the highest quality and best level of monetary applications? There's a lot of content on the whole NOTs debate and these kind of culture wars that are happening. I probably won't spend a ton of time on them, but it's an interesting kind of new perspective to look at this from. Okay, so overview of the whiteboard here. I'm going to discuss a little bit about, what I'm going to say pre-Bitcoin of like attempts at creating digital currencies before Bitcoin. I'm then going to talk about like what is really the core innovation that Bitcoin created, like what is the new novel thing that Satoshi did, which we couldn't recreate, previously. Then that'll be a nice segue into understanding client-side validation, which is a off-chain, protocol that some people are building. Then we'll go into shielded CSV, which is kind of like the core innovation that we're talking about here about adding perfectly private payments to Bitcoin. And then, we'll kind of high level discuss a bit about like where I think the end game is going to be and how shielded CSV interacts in this kind of broader landscape of, L2s and Bitcoin and ZK verification and scaling, etc. So let's go ahead and hop into it. So before Bitcoin, so pre 2008, let's assume that there are two parties. There's Alice and Bob, and they want to send a transaction of some sort of digital currency to each other. So we can just set this scenario and say like, all right, we want to subtract 10 units from Alice over here and add, 10 units of some random currency over here. Well, we could already do this with the existing cryptography, which is like public-private key cryptography and digital signatures. Specifically, we could, or Alice, I should say, can craft a message here of just like, I don't know, we'll just call them coins, just like some arbitrary type of currency. They can create some sort of message, just any sort of data, and then they can sign this. Alice is going to sign it as David. And what public-private key cryptography allows us to do is basically conduct this exact activity with what we'll call authenticity authenticity plus integrity. Okay. So what this means is that we can have cryptographic assurance that we can craft a message that is tamper-proof. That means that it can be sent from Alice to Bob. Bob can have assurance that this message was not like modified or manipulated, and we can check the kind of digital signature to verify that that is true. Again, that it has authenticity and integrity. So this is kind of like the quintessential building block to saying, well, we could just build a currency. Like we can build payments off of this. Like people can just, write up these notes, these digital notes, they can sign them, and great, we can like add, subtract currency from people, and we're all done. The potentially obvious limitation here is maybe you've heard the term like double spend or like the double spend problem. So even though we have authenticity and integrity of this kind of setup right here, somebody, Alice in this case, could double spend this transaction. They could copy paste, copy paste, copy paste this, and they can spend it, two, three, four times. We call it the double spend problem, but they could spend it an infinite number of times. So this was the kind of main limitation as to why all other prior attempts at creating, digital currencies failed. The naive solution to this is really pretty simple. You just need some sort of ledger, or you can think of it almost like a public bulletin board where people can, take these transactions and post them into the ledger or into some sort of, public space. That way that if they ever try to spend these transactions again, somebody can go look on the ledger or the bulletin board and be like, nope, these transactions have already been spent. This is not valid. Like we are not going to allow this payment to be accepted. The problem is who controls the ledger? Who controls this public bulletin board? Can it be censored? And so that was a kind of this like unsolvable problem that Satoshi ended up solving. So when Bitcoin came about, its main innovation is really solving this double spend problem. It was creating this censorship resistant, immutable public ledger. And whenever we talk about things like miners and proof of work and difficulty adjustment, much of the innovation there, again, is more so about like the game theory and the economics of creating this decentralized system for ensuring that stuff has not been double spent, rather than some sort of innovation on the cryptographic side. I won't spend a ton of time on this, but an example would be you have miners in Bitcoin. These are entities that are taking their machines and they're pumping in very expensive electricity and energy, and they're trying to win the competition to get the next Bitcoin block. And so that is a real world expense that they are spending, is to mine Bitcoin. And so if they're fortunate enough to win the block, what they're doing is basically going to the mempool and they're taking things that look like this, like these transactions with, digital signatures and coins. And they're saying, we're going to put this into the Bitcoin block, and they earn fees for that, or they earn the block reward. So miners put in expense, which is energy. And if they follow the rules, then they receive money and it's a profitable venture. Now, if the next miner mines a block and they also try to put this same transaction in when it's already been in the block before, then this would be a double spend because it's on this kind of public ledger and everyone can see it. Then everyone would be like, why would you do that? Like we're just going to reject this block. So a miner would try to put it in this block and it would be rejected essentially by the network, and everybody would just continue on with the next block. And so in this case, the miner expended a lot of money. It cost them a lot of money, but they didn't get any sort of reward because the network rejected it. These are the type of mechanisms that allow Bitcoin to work. The scope of that is maybe for another video. But the takeaway here is really Bitcoin is meant to do one thing and one thing only, which is like provide double spend protection in a censorship resistant manner. All the rest of this stuff, digital signatures, public keys, private keys, yada, yada. We just like Satoshi just happened to put this into the Bitcoin network, and your nodes just happen to also like validate these transactions and check these signatures, but that's not really the core innovation here. So that leads us to CSV, or client-side validation. I think over 10 years ago, one of the OG Bitcoin developers, Peter Todd, kind of acknowledged and realized what was going on here. And he said, hey, there's a whole bunch of stuff that Bitcoin nodes are doing right now that they don't technically need to do. So why don't we just move all of that off chain? And why don't we only put the minimal amount of information onto Bitcoin that we need, which is this kind of double spend protection? So Peter Todd was kind of the OG pioneer, at least as far as I know. It was then picked up and promoted by people like Giacomo Zucco. And then it was picked up by Maxim Orlovsky, who's part of, RGB. And then if you've heard of like Taproot Assets, formerly known as Taro from Lightning Labs, that's also based off client-side validation. So all of those people and products are kind of in this family of client-side validation. So let's go over how this works. Let's assume we have a similar scenario here where we have Alice who wants to send a transaction to Bob. And let's say that they want to send 10 units of something right here. So the way we could think about this is Alice would craft a transaction to Bob. And again, similar to above, you would have some amount of coins. And let's assume that it's not just like one account balance that has 10 units. You have like multiple different coins. And like all of these different coins in the stack add up to 10 units total. And so each coin within the stack has a different, transaction history. Like they were minted into existence. This was like their earliest genesis. And then they were sent here and here and here and here and here. And eventually they ended up in Alice's wallet. Like every coin in this kind of stack, I have like a stack of these here, has some sort of history. And so for each coin, you may have something that looks like this. You have like transaction 1 when it was minted into existence, and it was sent to a person, and there's like a digital signature here corresponding to that transaction. And then transaction 2, you have like another digital signature. And so each coin is going to kind of have this like history of transactions, which kind of prove who actually owns it right now. And so what is happening in a client-side validated protocol is you can almost think of this as like every time you send a payment, there's like a folder, and you can open up the folder and there's all of the coins in there. And then there's all of the supporting documentation for each corresponding coin that says like, here's when it was minted into existence. And here's all of the prior provenance or the, like the history of that coin. And the receiver of this doesn't need Bitcoin whatsoever. They can look at all of this supporting documentation and they can confirm that all the coins that they're receiving are like have a validity, or that they can trace their transaction history, so that they know that this person, Alice, did in fact actually own these coins and is in fact actually sending them. So this is kind of where we get the name client-side validation, because all of this process of checking what's kind of in this folder and checking the provenance is happening on the client side outside of Bitcoin. And when I say the client's checking it, I don't mean like literally you're checking it on your computer and like an Excel spreadsheet or something. It's like the wallet that you're using, or like the computer software will essentially check all of this. The whole point is just so like you don't need a Bitcoin node to actually do this. But similar to the problem up here, it's like, great, okay, we can check the kind of validity, we can get the authenticity and integrity of the transactions, but like, how do we know if these are double spent? Well, what we can do is we can take that kind of that metaphorical folder that I told you about that represents like transaction and all the coins inside of it, and we can feed it through a hash function. A hash function will take any amount of data, whether it's large or small, and it will compress it into a fixed string of characters. And if anything changes with this data or this folder, there's like one additional dot here or one transaction, like any small thing, then the hash will essentially change. It's almost like a serial number, and that serial number will change. It's unique to that kind of specific folder and all the data inside of it. So we can hash this, and sometimes this is also called a commitment. And you essentially can post this up into Bitcoin. And so I think in Taproot assets and traditional CSV protocols, this is like 32 bytes. Okay. And this essentially gives us the double spend protection, because a person, Bob in this case, that's receiving all of these coins, again, they can validate it client side, and then they can hash that very easily. And they say, okay, here's the SKU number I get that's corresponding to all of these coins or this payment that I just received. And they can check the Bitcoin network and say, does this hash exist? And if that hash exists, then it means that those coins have already been spent. So hopefully you can kind of see the logic here, that most of the logic we're able to do off-chain, the client-side validation, and then it's just a tiny little hash that we're using to anchor and get the only thing that we really need Bitcoin for, which is this like double spend protection. All right. Okay, so now let's talk about shielded CSV. Shielded CSV takes this concept. Oh, let me back up a really quick. So the downsides of client-side validation. There's a few downsides. One is no BTC, or I should say you need a bridge. Okay. So this protocol of client-side validation works with like other non-Bitcoin tokens. And that's why it's being used for things like Taproot assets, where they say we want stable coins. So they're going to have stable coins, and then they get the double spend protection of Bitcoin. The second thing is the transaction history growth. Okay. And the last thing I'm going to put here is privacy. So the major pitfall here is that if you remember here, it's like we have this folder, we open it up, there's a bunch of coins, there's all this supporting documentation for every single transaction that the coin has traveled. If you have a high frequency coin or payment token, then this transaction is going to grow. It's not just going to be transaction 1 and transaction 2, it's going to be transaction like 10,000. And that eventually becomes like too cumbersome and too onerous, and the protocol starts to break down. There are some solutions to it, but they're like probably a little clunky. Things like you take in the coins, you burn it, you remint it. It's not an ideal strategy. So this transaction history growth is an issue. And then the second thing is privacy. CSV has pretty good privacy because if you're only sending this transaction from Alice to Bob, unlike Bitcoin, not everyone in the network can see every single thing that you're doing, right? Only Alice and Bob would be able to kind of see in this because they're the ones that are kind of seeing and receiving this folder and checking like all of the prior history of the transactions. But as these coins travel to other people, those other people are going to have to see like what's inside that folder in order to get the validity. So it has better privacy than Bitcoin, but not necessarily perfect privacy. Where this changes is shielded CSV. So when we introduce this concept of ZK or zero knowledge, it alleviates the major problems that happen with pretty much all three of these actually. So the first thing is the way that a zero knowledge proof works is, if you've seen my other videos, I described it as like an unforgeable digital receipt. So you can have some sort of activity here where we have a similar setup where we say we're just trying to like deduct 10 units of something from over here, and we're trying to add 10 units over here. And so there's some like transaction that happened in the middle to facilitate this. And up here in Shielded CSV, it's like you list all of the transactions that get you from point A to point B. With a zero knowledge proof, you can take in these transactions, create an unforgeable digital receipt that mathematically proves that you went from here to here using a set of valid transactions. And it will essentially then delete or get rid of those transactions. And so this is really amazing because with a zero knowledge proof, where we replace or I should say we replace all these transactions with just a zero knowledge proof, you're getting validity, you're getting compression, and you're getting privacy. You're basically getting privacy for free. So the way this would work is that if I'm Alice, the user, and I want to send a transaction, I'm crafting a transaction, and then I'm creating a zero knowledge proof client side, like on my mobile phone. So it never leaves my phone. I never have to send it to an AWS server or some other big entity. I'm just crafting it on my phone, and then I'm deleting all of the contents related to that transaction. And then I'm just sending this zero knowledge proof, which gives the receiver mathematical certainty that I did in fact own those coins. I am now transferring them to you, and all of this is valid. Because we threw away all of the transaction data, we're getting this kind of compression because the proof is like very succinct and very small, and you basically just get privacy for free. So zero knowledge proofs are kind of like the ideal solution to the problems that client-side validation had right here. Okay, so the next thing, let's see. So this hopefully all makes sense. We move a ton of this off-chain. All right. So with shielded CSV, you still need to have this like double spend protection. So it's the same concept here. You're basically having some sort of commitment. You're posting it up into the Bitcoin layer 1. And in shielded CSV land, they just call these nullifiers. So nullifier. Okay. And these are like 64 bytes per transaction. So similar concept. We have some small amount of data, again, 64 bytes per transaction that gets posted up into Bitcoin. And that's how you know whether this stuff has been double spent. No amount of like cryptography, ZK magic can solve this double spend problem. And so that's why it's like we can pretty much solve everything with zero knowledge proof on this side, but we still need the nullifiers to anchor for double spend protection to Bitcoin. Let's see. And these are the pieces of data that get posted to where inscriptions normally get posted. So if you remember, I kind of started this about like the culture wars in Bitcoin. It's like, if we have this ability to post data on chain, that space is going to be used for dick butts. What I'm saying is like, this is a very credible use case that, gives us perfect privacy cypherpunk level payments and benefits from having the ability to post to the Bitcoin layer 1 so that we can inherit the double spend protection there. All right. So let's map out kind of very high level what this looks like. What I'm expecting is that shielded CSV will be built at some point as like a layer 2 on top of Bitcoin. So let's say we have shielded CSV right here. But if you remember, I said that CSV can't be used with Bitcoin, like unless you have some sort of bridge, like some sort of federation. So it's kind of like we can have this private transactions, but if we need a federation, it's like trusted, it's centralized. But that's where this ZK verification comes in, which if you've watched many of my other videos about ZK rollups and BitVM and Glock and how, we're kind of hacking in this ZK verifier into Bitcoin, that part is what's solving the bridge part. So if we have a ZK verifier right here, what you essentially get is you get a trustless, or I should say technically like absolutely trust minimized bridge that can bridge Bitcoin from the layer 1 up into this layer 2 perfect privacy payments protocol. So in shielded CSV, ZK is being used for this like compression and privacy and validity. When it comes to the verifier, this is what gives us like the very trust minimized or near trustless bridge to go from Bitcoin L1 into the L2. So it's ZK in both cases, but slightly different applications. And so we can expand on this, and I've hinted at this in prior videos where, we can have multiple different L2s and we can have like an EVM. And so a lot of the teams that you see building these kind of like ZK rollups on Bitcoin, they're saying, well, hey, we're building like an EVM compatible, layer 2. It's like, that's just one type of layer 2 that can be built. Like once you build the core infrastructure where you have a ZK verifier that can take in any sort of execution environment and you can bridge from the layer 1 into a layer 2 via the ZK verifier, then you could do that for EVM. You could do that for shielded CSV. You could do that for like a UTXO chain, and you could build like Lightning Network on this UTXO chain. It's like a fork of Bitcoin, maybe with Covenant's opcodes or something to make Lightning more effective. Or you could build like Arc up here, And all of these, when you put them into a ZK verifier, all of these can essentially speak the same language, and they can start to cross-compose and share liquidity in theory amongst each other. So, this is kind of like a very early idea, but this is the type of stuff that's possible. Like now that we can start bringing ZK into Bitcoin, we can get privacy, we can get scalability, we can get interoperability. Like we can get very close to having this end game, this grand vision. So I hope this whiteboard was informative to people. For me, this is like on the very bleeding edge of what's happening in Bitcoin, and where we can finally say, hey, you can actually start to build this stuff on Bitcoin. Not where we say, hey, come build on Bitcoin. It's actually like very clunky and you can't really build the things that you imagine. Like we are getting to the world where we can actually do it all. We can kind of like fulfill this vision that gives us all the capabilities. So that should be all of it. If you've made it this far, add in the comments, who wears the cowboy hat better, me or Jimmy Song? And if you have any ideas for new Bitcoin whiteboard videos, also feel free to drop them down there. All right. Thanks, guys.